What's up, guys? Mrs. Thompson here, and today we're covering thermochemical equations. Just a little bit of stoichiometry within thermochemistry. Alright, first word here is enthalpy. You need to know what that is. Enthalpy is basically the amount of heat in a system, and it gets its own letter, which is H for heat. There are different types of thermochemical equations. So different types of equations that have heat in them. Equations that are endothermic, where delta H is positive, which means you have to add energy in order for them to form products. In these equations, the heat is on the left side of the reaction, it's on the reactant side. We say that it's going into the arrow for endothermic. For exothermic reactions, there is a release of heat, and so you see a negative delta H because heat is coming out of that system. And so heat would be on the right within the thermochemical equation. It's on the product side. We're going to look at different ways to calculate enthalpy. And so there are three enthalpy types, or two enthalpy types that we're going to look at are enthalpy of a phase change or enthalpy of a reaction. Now, phase change could mean anything like melting or vaporizing or freezing, okay, or condensing. And then a reaction could mean something like combustion reaction. Okay. So here's our first example. It says calculate the energy required to melt 250 grams of ice. And then what's given to us is the delta H of fusion. So if you didn't know, delta H of fusion, or what fusion means means melting. Okay, so it kind of sounds weird. I know it's different than when you talk about fusion in the stars. Fusion actually means melting here. And so the delta H of fusion is 6.01 kilojoules per mole. We'll do some stoichiometry. And so what we'll do is we'll start with our number with its units. The delta H of fusion is like a conversion factor here. It's 250 grams of water. Now, what you have to do with these is you have to change them into moles because delta H of fusion is in terms of kilojoules per mole. So we'll take water and we'll multiply it by 1 over the molar mass so that you can cancel out grams. And then we'll multiply it again, but this time by the enthalpy of fusion, which is 6.01 kilojoules for every 1 mole. So 1 mole of water would give me 6.01 kilojoules. Cancel out moles, and we just do the stoichiometry as usual, and that's 83 kilojoules. Okay, so we could have enthalpy of solidification or freezing. We could have the enthalpy of vaporization, and as long as it's written as kilojoules per mole, we would treat it exactly like this. Okay, example 2. How much heat is required to consume 54 grams of CO2? And so the balanced chemical equation is written here. Should be something that you recognize. You've got carbon dioxide plus water plus some energy which comes from the sun to produce glucose and oxygen. Hopefully you said photosynthesis. Okay. So we need to know, is this reaction an endothermic process, or reaction, or an exothermic reaction? And so we look to see where the energy is at in the equation. Here it's on the left side, which means it requires energy. You have to put heat in. Heat is going into that arrow there, and so this is endothermic. And so delta H would be a positive 2808 kilojoules. So what that means is that you would need this many kilojoules for every 6 moles of carbon dioxide or 6 moles of water. Okay, or you could even say it in terms of the product side. You would need this many kilojoules to produce 1 mole of glucose or 6 moles of CO2. All right, so let's see. We need to consume 54 grams of CO2. So that's where we will start. Oh, and by the way, that means endo. All right, so 54.0 grams of CO2 times. Well, we need this in terms of moles. So we're going to have to change the grams of carbon dioxide to moles of carbon dioxide. We know that the molar mass of carbon dioxide is 44.01, and that's for every 1 mole of CO2. That cancels out grams. And then we have one more step. We're going to say that the amount of energy is for the moles there. So we have CO2. So in front of CO2 is a 6. We're going to drag that down over here and write 6 moles of CO2. And so for every 6 moles of CO2, we need this amount of energy. Okay, a little different here. This is like your mole ratio, but it's like a mole to energy ratio. Okay, so then the moles cancel, and we do the math, and we get 3,450 kilojoules. One more, example 3. Determine the mass of iron used to produce 250 kilojoules of heat according to the balanced reaction below. So in this case, we have the energy first. Okay. And so we have the equation for iron rusting, forming iron oxide. So iron plus oxygen makes iron oxide, or iron 3 oxide, plus some energy. So this is an exothermic reaction because heat is on the right side. It produced that heat, it gave it off, so that's negative delta H. And so I'm going to write that on the side. Delta H is negative 1,625 kilojoules. And so that's for every 4 moles of iron, 3 moles of oxygen, 2 moles of iron 3 oxide. Okay, so we'll start with the energy this time, so working backwards. Oh, and that's exo. All right, so negative 250 kilojoules. And it is negative because we are producing that energy. Okay, so we're producing that energy. We want to cancel out kilojoules. So we need kilojoules to go on the bottom. And that negative 1,625 kilojoules is going on the bottom. Great. That's for every 4 moles of iron. Remember, that's coming from the balanced chemical equation. For every 4 moles of iron, you get this much energy. Okay. So then kilojoules cancel. We want to know the grams, not the moles, so we'll do one more step using the molar mass. 1 mole of iron is 55.85 grams of iron using the periodic table, and that's 34 grams. Notice my mass is positive, which is good because we don't have negative grams, right? So that negative here cancels out this negative here. And that's it for today. So hopefully you found that pretty easy. See you next time.